The Flash. Welcome to CS302 assignment 4. And I got the inspiration for the assignment during the Super Bowl. There was a Flash commercial, and the movie comes out actually on my birthday, so I was even more excited. And of course, there was much more to that trailer than just the Flash, but I don't want to ruin it in case you haven't seen the trailer just yet. So, as you know, the Flash is a character that can run really fast, and I'm not a hardcore Flash I don't know much about the Flash, but I know he runs fast. But of course, there are some scenarios where he runs so fast he can go back into time and mess around with the space-time continuum, mess around with the past, which will alter the present and future. So for this assignment, you're going to pretty much have a binary tree. And I guess the Flash is going to have several, so these nodes in the binary tree will be locations. And of course, the edges of this tree, so the two children pointers, will be paths that the Flash can take. And you want to, given sort of a binary tree, you want to find the path that has the largest zigzag formation. So Flash could go through all different paths, but you have to write a program that will help the Flash, where it gives the Flash the path, and the Flash takes that path, which will be a big zigzag. And I guess in this case, a big zigzag formation is going to allow the Flash to really kick into high gear and go really fast and go back in time. So that's sort of the theme of the assignment. So that's like the preliminary content there. Let's go ahead and now discuss the actual contents in the class, this binary tree class, and so on. Okay, so this is going to be the contents of the header file. So I'm going to be using a string and a vector. Now each node I'm going to use only a single character. I'm going to store a character into each node. So really a character type would have been good enough. But originally I thought about using strings and I sort of scrapped the idea. But I still kept the string type anyway, so it's not really much of a problem to use string type. And of course I also included vector into this header file as well. So right here we have this binTree nodes. As you know, each node of a binary tree contains sort of a data field. So the location will be a data field. Now, each location will be just single character because I wasn't too creative enough to create different natural names. So there will be just characters A, B, C, up to Z or Z. And of course, you have your left and right pointers, so our standard binary tree node. And then here's going to be our binary tree class. So I'm going to, of course, quickly do a quick rundown of this class. And I'm going to then go into some details as to how you would construct the binary tree and write this algorithm to compute the zigzag. Now, you're not going to be able to modify this header file. And in fact, on CodeGrade, it'll be set up where I already have a header file already in the fixtures on CodeGrade, so you're not going to be able to submit anything other than a binary tree implementation file. Also, I'm going to give you a main as well, which I will link the main in a header file on Canvas. But of course, it will be already in CodeGrade, so you have to only submit the implementation file for binary tree. And then, of course, it will link the header file and main to your implementation file and so forth. Anyway, let's go ahead and discuss the binary tree contents. Now, of course, I do have a write-up portion over here, which you can, of course, read through, but I'm going to, on the board or on OneNote over here, talk about some of these contents in a little bit. So anyway, we have our root pointer, which, of course, will be our root of our binary tree. No surprise there. Then we'll have our constructor, our default constructor, which basically all it does is sets the root to equal to null pointer, just to make sure we initialize the binary tree correctly. Then we have our destructor right here. And you might also notice we have a deallocate tree function right there. So this destructor is going to call deallocate tree and will pass in the root pointer. And then of course, this function deallocate tree using a post order type traversal is going to deallocate each node of the binary tree. So if r equals null, return. If it's not null, then you deallocate r left, deallocate r right, and then delete r. So I gave it away, but that's fine because there's not really too much to the destructor for a binary tree. So now we have these two BuildTree functions. So I have this one right here defined. And of course, I have this one right here, which is going to be this overloaded BuildTree. So in main, this BuildTree gets called. And of course, this BuildTree function makes a call to this BuildTree function right here, which is going to be a recursive function. And you also will notice that it returns a pointer back. So it's going to be relatively similar as to how I show you in class as to how a binary search tree insertion sort of works. So this BuildTree is going to be recursively will insert all the nodes into a binary tree. So what happens is in this function, we pass in a vector of locations, and that vector contains a tree in this level order sort of setup. And you have to, using pre-order, you have to build a tree. Now, of course, I'll give you a nice visual example as to what I mean by that. But this function will, in main, I read in the input from the user, and I create a vector of locations, and I pass that into the BuildTree function. And you have to, of course, write this recursive BuildTree function, which will parse through that input, that vector of strings, and it will insert nodes one by one into your binary tree. Then, of course, the last portion is going to be this ZigZag function right here. So this is going to essentially return a vector of all the nodes in the path that creates the largest zigzag. So in main, I call the ZigZag function. This ZigZag function in the function body sort of processes the root node, and then a root node actually has to call this other zigzag, the overloaded zigzag function. And this zigzag function gets called on roots left and roots right. And of course, this function recursively will constantly build a zigzag path on the left and right side of each node. And then once a return gets returned back, you have to return the bigger path among the two sides up to the parent. So that's a very quick rundown of how this works. So now I'm going to go ahead and talk about just some more details, and so you can visualize how BuildTree works and how the ZigZag function works. So this is going to be an example binary tree you might encounter. So the input, so that vector that we pass into the BuildTree function is going to be this vector right here. So notice how each block is going to be a separate index of this vector. So you want to sort of create this tree given that vector, and the vector is going to really store the tree in level order. So our first level will be that node A by itself, and then level 1 will contain B and C, and in level 2, well, for this node B, it has no left child, so we can sort of just have an understood or sort of an implied underscore right there. So underscore means it's a null child, so these 4 nodes right there are going to be part of level 2. And in level 3, of course, we can assume that, well, we have null over here. D has 2 null children, E has a right child as null, and F has 2 null children right there. So we have 4 dashes in a row, followed by a G, then we have 3 dashes afterwards. So we can see this is going to be our level 0, level 1, level 2, and level 3. So the input is given to you like this, in this level order traversal. So you want to go ahead and now be able to create this binary tree, and you have to parse this input in a pre-order kind of fashion. So let's go ahead and now just talk into more detail as to how you want to recursively use pre-order to construct this tree given this input. So in the BuildTree, the public BuildTree function, this is going to be the only line of code you would probably need to have in that function body itself. So when you call a function recursively, or you call this recursive function right here, you pass in a brand new node. So you're passing in the address of a newly allocated node. You pass in the locations vector, and you pass in the index. Of course, index 0 will be the root node. And of course, the result of this BuildTree function is to return a node, and root will catch it. So this node I pass into the function, this node is going to get processed, and at the end, we're going to return this address of this node back, and then root will catch it. Now, if let's say we hit the end, this node should be deallocated in that new function call. So I'll kind of highlight that also as I go through this. So first thing we do is our R parameter. So I'm going to go ahead and just have an R parameter defined right there. It's going to be assigned to a node. So right now, I'll put this here in blue that we're at index 0. So we check 0 is not beyond the bounds of the vector. And index 0 contains a, which is not underscore, which means this is not going to be a null node. So we're going to, of course, assign, I guess I'll use red. I'll assign a right there. So of course, you just do r arrow locations equals, r arrow location equals locations at this index, which is whatever this is going to be. And now, in this function body, we want to recursively call BuildTree and then assign r arrow left equal to BuildTree and then r arrow right equal to BuildTree. So same idea, in this function where r points to that node, we're going to do exactly the same sort of work like this. I'll kind of give you the code here just to give you an idea. So you would have r arrow left equals BuildTree. I don't have space for this whole thing, but you'll pass in a new node. Sorry, binTree node. You pass in the locations vector. And in that function body, you have a parameter called index. So always the left child always will be at index multiplied by 2 plus 1. That'll always be the location of that left child, no matter what. And then, of course, afterwards, you're going to go ahead and say r arrow right equals BuildTree. And I guess I'll have to two-line this again. So you pass in a new node. Pass in the locations. Now the right child always will be at index. Index, I think it's index plus 1, multiplied by 2. Will always be the index of the right child for at any level. So if you follow this pattern, you'll be able to always index, because we can see here, in this case here, if you look at it, A's left child will be B. B's left child is going to be this empty element right there. And then A's right child will be this element right there. And then C's left child will be E and right child will be F. So that formula does kind of hold. So it's going to be E and F. So it's going to be essentially index multiplied by 2, which is going to be 4 plus 1, 5. Okay, perfect. And of course, 2 plus 1, 3 multiplied by 2, 6. So yeah, this is going to exactly index the correct child, essentially. So let's first process the left side. So what's going to happen is a new node gets created. And R will be assigned that. And we're going to pass in index of 1 is being passed into this function. And of course, you pass in the locations vector as always. Okay, so looking at index 1 contains, 1 is not beyond the bounds of the vector, and 1 does contain a non-underscore. So that means we have to process this node right here. Right B, right over here. And now we have to process this node's left and right side. So you can see we're going to be constructing this in pre-order fashion. So of course, left side will be first. So since we're at index 1, the left index, we're going to go ahead and we're going to call BuildTree right now, pass in a new node, which will spawn a new parameter R. And to this function, we're going to be passing in, let me make sure I'm correct right here. So for B, it's going to be, the left child will be right here. So it's going to be a blank. So it'll be 3. Okay. Just so I don't make a mistake. So B has no left child. Okay, perfect. It's hard to do math in my head sometimes. So that's going to be the scenario. So we see here, okay, so index 3, is it beyond the bounds of the vector? It's not, but index 3 contains a blank, which means this has to be a null node. So you would have to essentially just deallocate R. So delete R, you want to deallocate it, and return a null to the parent. So the parent, which is going to be the previous function call where R points at node B, its left pointer will be assigned with null, because this function returned a null. So that essentially means that B's left child will be just assigned to null, which is what we wanted it to do. So the next step in this function body, we first did left. Now we have to, of course, process this side for when r equals that node B. So we have to, of course, allocate a new node, have r point to it, and this node's index, so it's going to be essentially, let's see, B is 1, so it's going to be 4 will be the index, right? Because 1 plus 1, 2, multiplied by 2, so it's 4. So we pass in index of 4 into this function. See what happens. So we jump up here. Index 4 is not beyond the bounds of the vector, and index 4 contains letter D. So we're going to go ahead and write D right in here. And now for this function call, we have to first process the left side, then the right side. Again, this is more pre-order, very boring stuff once again. So we have to call BuildTree r left. We're going to pass in a new node, and this r node, this a parameter gets spawned right there. And we're going to be passing in, so we're going to pass an index multiplied by 2, so we're going to pass in 8, and so 9, we're going to pass in 9 into this function for the index. We're going to check the index in this function body. Index 9 is a blank, which means, okay, D has no left child. Let me make sure I'm correct here, and that's true. D has no left child in this case. So we're going to obviously deallocate this node and return a null pointer back. So then D's left pointer will be set to null. Then we have to process the right side. So again, we call BuildTree. We pass in a new node object. And we're going to pass in the index of, let's say, 4 plus 1, 5 times 2 is 10. We pass in 10 into this function body. Now let's go ahead and run this function. So let's see, when we have 10, we're not beyond the bounds of the vector, but index 10 contains an underscore right there, which means that's a gap in the tree, so it's a null. So deallocate by just delete r, and then return null back up. So now D's left and right side has been processed. So that means in this function body where r pointed as node D, we processed both of these. So the last thing we have to do is return r. The same way we insert into a binary search tree from the example from last week. So we're going to return the address of this node up the tree. So we go to the previous function call. This function call is now over, so r doesn't exist anymore. So neither do these r's also don't exist either because we're out of that function body. So what happens here is that we last left off on that line when we had it where r pointed to that node B. And then this function call returned the address of this node. So r right will be assigned to that node. So B's right side is going to be D, which is consistent with our initial picture. And then for this function body, where r points to this node B, we just did this. So the next thing we have to do is just return r. So return the address of this node up the tree. So we're going to, this r is now going to be gone. We go to the previous function call. The previous function call was where r points to this node A, and we were last left on that line. So this function call returned this node's address, so r left will be linked to that node. So we can see here that A does in fact point to B, so we have to resume. By now calling for this node where r points to A, we have to now process this line. And once we finish that, we're going to return r, and then this node right here root will be assigned to point to that node A. So of course, I think I'll leave it right there, but that's really the idea. So of course, I kind of gave you a little bit of help there because, well, of course, if you don't have a tree constructed, you really can't do anything. So I'm hoping that this gives you an idea of how to construct a tree. Once you have that, of course, you can verify if it worked by, you can just maybe, well, I guess you can locally in your own, you can copy a header file I provide for you on Canvas. You can update it temporarily just to sort of have your, you can create a pre-order function call you can create that outputs nodes and pre-order forms. You can verify if it did correctly insert. So of course, you can, you can add that to your own custom header file, but then remove that before you upload to CodeGrade, or else you'll get compiling errors. But you can do it locally just so you can debug and make sure that everything is correctly inserted into your binary tree. So the next step, or a final step, is going to be going over the ZigZag formation. Let's go ahead and talk about that part next. Okay, so let's consider this example right here. So when you first call ZigZag in main, you pass no parameters into the function. So clearly the only pointer you can look at is just the root, which is of course the beginning of any possible zigzag in your tree. So you want to, of course, make your code scalable, where you recursively traverse this tree. So you don't want to you don't want to hard code this, but you can, of course, see from node A, is there a zigzag so far? So of course, the root can check the left and the right child to see if there does exist a left and right child. Also, you can verify from A if A has any grandchildren, because also that's going to be constant, because look up whether A has a left and right child, and if A has any grandchildren is very easy, because every node will have at most 4 grandchildren and at most 2 children. So of course, in constant time, you can quickly verify all of that. So looking at this scenario, where the red is your children of the root and green is going to be the grandchildren of the root, can we see any possible zigzag right here? And it looks like this forms a zigzag, whereas this does not form a zigzag, neither does that. But this path right here forms a zigzag so far. So you can, of course, figure out which node is going to be the first node in a possible zigzag. So what you do here is you're going to, of course, you're going to have to do this in pre-order fashion. You're going to have to go ahead and first process the left side of A, then the right side. So whenever you call a zigzag on the left and on the right, the two returns, they're going to return back to you a path. That vector that returns is going to be the vector of nodes in a zigzag path. And of course, you have to return back to main the bigger path. So let's first begin. So you first call zigzag, the parameterized zigzag function. You pass in this pointer r, and you have that one boolean called child type. So true would imply that it's a left child and false is a right child. So of course you pass in true into this function because B is a left child of its parent A. And also, since A's left side, we already determined we had a zigzag earlier, we can of course pass a vector into this function that contains only a single node. So that means A is going to be the starter of a possible zigzag. So now at this node R, where R points to B, you want to verify if any zigzags are possible. So we can see here that, well, there are no zigzags possible because we only have 2 children, and these 2 children, maybe I'll be consistent. So here's the children of B, and then their grandchildren are all empty. So we know for sure there's no possible zigzag any further. We still have to go through the motions anyway. So we see here that, okay, fine. We see that there is no zigzag on the left side. We still have to try the left anyway. So of course, what happens here is for B, you of course pass in the left pointer. You pass in true again. And this time you're going to pass an empty vector into this function because there is no path. So this is kind of a dry run, if you will, because there's not going to be anything found here, but we're still going to go through the motions because we have to make sure we're consistent, because recursion is very specific how things work, and we want to just sort of go through the motions just to like make this work. But of course, you can sort of hard code certain parts, as in you can like cut off the recursion on one side beforehand, but I'm doing a more general way of doing this. So right now we see that for D, we see that D has no left or right child, but we'll still go through the motions anyway. So what happens here is you're going to go to the left side of D, which contains null. We pass in true, we pass an empty vector. And since R is null, we're going to return back an empty vector. Now, the right side, the same thing happens, except the right side, we're going to have, again, R will be null. We pass in false because this null is a right null of D. And of course, you pass in an empty vector again. And it's going to return back immediately an empty vector. So D has not been fully processed, so you return empty vector back to B. So B has determined that the left side is empty, which means that there was no zigzag on B's left side. Okay, so now we see, looking at B, in B's function scope, that vector contains a node that contains just one element, A. Or sorry, that vector contains one element, A. So now what we're going to have to do is go ahead and go to the right. Now we see here, since B is a left child of A, because that's true Boolean, that means if you go to the right, we are going to, of course, we're going to obviously see that we have, a possible zigzag. So we're going to go to the right side over here, and then we're going to have R point to this node. We pass in the false, and we're going to actually pass in a B into this function, because we first determined that A was a zigzag. We go to B, and since B is a left child and B has a right child, we of course tack on. We call the function again, but we push B into that vector that we're going to pass in. We pass an AB into this function. Now for E, obviously, what's going to happen is, since E is a right child, because of its fact that it contains a false for that parameter, we're going to go to the left. We're going to go ahead and pass an E's left pointer, which of course is going to be a null. I'm trying to fit this in over here. And since it's a left side, we're going to, of course, we're going to pass in a Boolean true, and we're going to actually pass in a BE into this function, because it's a left side of E. And since this pointer R in this function call is null, we're going to return this parameter back, ABE back up. So now E's left side, it returns ABE. Now if you go to the right side of E, what happens is, in E's right side, we see that E has no right child. Therefore, E cannot start a zigzag, because E has to have a right, and then E's right has to have a left child. So E has to have a right, and the right has to have a left. And since E's right is null, that means we don't have to even recur. So we can just say, well, return, we can just sort of assume the right side is already null. So for E, the right side was empty vector. Left side contains 3 elements. Of course, return the bigger one up. So return a BE up. And now for B, what's going to happen is that at B's level, B's left returned an empty vector, and B's right returned a vector of size 3, so return a bigger one. So at the root level, where our root is, points to that node A, the left side, we found a zigzag of 3 elements, A, B, E. So now we have to try the right side next. So I'm going to sort of just kind of begin this a little bit. So the right side, we're going to pass in this R parameter. We're going to pass in false and pass in an empty vector, because at this moment, A cannot possibly be the head or the beginning of any path that's a zigzag, because we have A's right child's left is null, so A cannot be in a zigzag right there. So now what happens is we're going to start a brand new path over here. So C's left side is blank, but the C's right side contains a node, a child, and it has two children, one to the left, one to the right. Therefore, we detected a zigzag, at least the beginning of a possible zigzag. So that what happens is, okay, fine. I'm going to go ahead, do that. We're going to go ahead, and this time we're going to go ahead and pass in an R parameter right here. Pass in false. I'm going to pass in C into this vector because I can determine that I do have a zigzag. So you always verify if a zigzag is possible, and once you find a zigzag, then you kind of create this Congo line along this path when you alternate between left and right and so forth. If it's a null, that means there was no zigzag found earlier, so maybe this new node you entered into could become the brand new, could be the first node in the possible zigzag. So essentially, if you pass an empty, so that in this case, when I pass empty vector into this node C, that means that there was no zigzag determined earlier, but maybe C might be the root of its own possible zigzag, which we see right there. So anyway, hopefully this was not too confusing, but I'll leave this open for right now, but that's how you want to think about this zigzag problem. Okay, let's go ahead and go over some final remarks, and then this video will be done. Okay, so as mentioned before, you are provided a main and a header file for your program, but of course, so anyway, when you submit to Canvas, you only have to just submit the implementation file, so your binTree.cpp file. But of course, I will have the header file and the main file on Canvas as well. So of course, you can download that. You can mess around with it for testing purposes, and of course, you can modify the class as you want for debugging. But when you submit your binTree implementation file, make sure all the functions in that file match the signatures for the header file to avoid compiling errors. So of course, document your code as always. Make sure you have no global variables, and really free is always important. So make sure you have those taken care of. And here are some sample outputs. So on the code grade, I might provide some more input and output. I gave a couple of simple ones right here, but any input and output that's used on code grade, I'll provide that for you also in Canvas. So you can just use Linux redirection to redirect the input into your executable, so you don't have to type out all of this every single time. This is a pretty big file. So of course you can redirect the file if you want instead. So if my program, of course, I give this funny message, Flash says Excelsior. A little humor, I guess, to the late Stan Lee. I mean, he does have Deadpool, which is a troll for the DC universe, because I think they have Deathstroke is Slade Wilson. Of course, Deadpool was Wade Wilson, and of course, and among other things too. So a little humor right there to the late Stan Lee. So in this program, it reads in these inputs, and then of course, it's going to call BuildTree and pass this in a vector form. And then it calls ZigZag, and your program has to return a vector that contains these elements. I run my program again. I have a bigger one this time, but of course, you can redirect the input into your program. And of course, here is the path. So anyway, that sort of summarizes up this video. Hopefully the video did help you. So I guess happy coding, and until next time.